Good afternoon, class.
Good afternoon, sir.
Good afternoon, sir.
So I think it is 5 minutes past 12. I think we can start now. So, about a good number of you are not yet around. But if we continue to wait, we'll be unable to cover what we have to cover. I hope you got my email.
Yes, sir.
Yes, I only had from I had only two feedbacks to say they got the email. And I've also posted an assignment on the course page. So I advise you go to the course page and submit the assignment before deadline. So is there any question from our last class? Do you have any question? So I've tried to make the course page a little more interactive. I have created a forum. I think that discussion link I put there is not very attractive. So there is a for every challenge that you have. And when somebody creates a question, it's not necessary that I must be the one to even respond. So it's like a discussion forum where you all discuss, and the discussion should be centered around the course or the topic that is of interest. So I hope you can see my screen.
Hello.
Hello. Can you see my screen?
Yes, sir. I have a question, sir.
Okay, I'm listening. What's your name and what's the question?
Regarding the assignment you gave us,
yes,
you left a 50-word page, like it can only take 50 words. So I'm asking, do we need to put our matric number because it won't be enough?
How many digits is your matric number? Should not take more than 1 word. So even if you must put your matric number, that is a word. So I don't see the excuse.
But is it important to put? Is it important to put the matric number, sir?
It is good. Time you should start with your matric number. The question. If you tell me 50 words is what, if that will make it be enough. It's the PDF now on the LMS that we are working virtually. It's good to check your email regularly so that, because if you have there is any information to be passed across, the email and the LMS platform are the notice boards that you can use to get across to ourselves. And even the advantage of working virtually is that you can always contact me even if you are shy or anything. So I think I've answered your question. So 49 words is not too. 49 words is not too small for you to answer that question. So in the course materials I use for this lecture, they are Introduction to Solid State Physics by Kittel, and the Oxford Solid State Basics by Simon, and Solid State Physics by Ashcroft and Meming. And mostly for the cost structure, I'm using that of number 2. And and it's very similar to what you will see even in your notes, in the class notes that I upload. It's very similar to that of Simon. And a lot of figures and tables I've extracted from that Simon. So in the last class, we spoke about solids, specific heat capacity of solids, and we went to the fundamentals to remind ourselves that the specific heat capacity here is talking about the heat required to raise the temperature of a particular material by 1 Kelvin. But that is heat capacity. But for specific heat, we have to specify: is it 1 kilogram? Is it 1 mole? Or is it 1 atom? So for us to say specific heat, we have to give a unit to how large is that particular solid that we want to, that we are talking about its specific, that we're talking about its capacity. So if I say the heat capacity of a material is, I can say 500 joule per Kelvin, but the specific heat will be per joule per Kelvin and also per kilogram. I'll be talking about per unit mass. But for this course, we'll not be talking in terms of per unit mass. Rather, we'll be talking about per mole or per atom. So when we are talking about per mole, that is when we talk about the universal gas constant, which is R. And when we are talking about per atom, then we'll be using Boltzmann's constant. So in the last class, we spoke about the definition of heat capacity, specific heat capacity, and how it applies to monatomic gases. And we moved on to solids, where we spoke about the law of Dulong-Petit that says that the specific heat capacity of solids is 3 kb. So, and we said the capital N is, the capital N talks about number of atoms, while the small n talks about the number of moles. Okay, so the capital N number of atoms, small n number of moles. When we are using moles, it's usually in terms of R. And when we are talking about number of atoms, it's usually in terms of Boltzmann's constant. So in the Boltzmann's model of solids, it was able to model or to reproduce the law of Dulong-Petit by the use of statistical mechanics. And the law of Dulong-Petit, which we have said earlier to be 3 C over N equal to 3 kb. So the law of the Boltzmann's model was able to prove the law of Dulong-Petit. However, the law of Dulong-Petit do not hold at all times. It does not hold at low temperatures. The law of Dulong-Petit holds at room temperature, but it doesn't hold at low temperature. And even for some materials like diamond, the law of Dulong-Petit do not hold at room temperature. But Boltzmann's model, unfortunately, was unable to tell us why. How? Why is it that way? Why is it that the specific heat of diamond is different from 3 kb? Then we had spoke about the Einstein's model. The Einstein's model also used a quantum mechanical approach to the work of Boltzmann, and considered a one-dimensional harmonic oscillator that is defined in equation 1.7. So this formula tells us the eigenstate for a single one-dimensional harmonic oscillator. So since we have said a single, we are talking about one atom. And the small n here is not, so this small n is talking about the energy level. I would have loved to use another symbol to represent this n so that you're not confuse it with a number of moles. But this small n here tells us the energy level, which may be, which is an integer, of course, and one, it may be 1, 2, 3, 4, 5. And so the energy level corresponding to 2 will be E2, which will be equal to h bar omega 2 plus half. So it's a very straightforward equation, and that was the approach of Einstein. And the partition function, which is defined as Z1d, was used to determine some other properties of the material, which especially the expectation energy. The expectation energy, which is was derived from the partition function, the expectation energy, which was derived from the partition function, was used to have this equation 1.9. And when we have the energy of the system, when we know the energy of the system, we can easily determine the specific heat capacity. When we know the energy of the system, and in this system, it is for a single particle. So that is why we can talk about specific heat capacity. So for this system, when we differentiate with respect to temperature, we can see temperature. So this function, when we differentiate this function with respect to temperature, what we'll be talking about will be specific heat capacity. So what we are talking about is to say that C will be equal to, I think we said something like this, dq dt. So if we say C is equal to dq dt, dq here is talking about like the quantity of heat or energy, which is E in this situation. So if it is E, then easily we can say that the E dt and the expectation energy with respect to temperature will give us the specific heat capacity. And the C here is as good as C over N, because N is 1. We are talking about a single particle for a single particle system. I think we said that somewhere here. We spoke about a single. It's one thing to be single. It's another thing to be one-dimensional. One-dimensional in the sense that it is easy to describe a system in one dimension. If we understand the system in one dimension, we can easily extrapolate and determine the behavior of the system in 3 dimensions. So we are still talking about what we did in the last class. So like I've said earlier, after differentiating the previous equation of expectation energy with respect to temperature, we have equation 12, which is the specific heat capacity. The specific heat capacity, that is differential of expectation energy with respect to temperature. So this is as good as we having a general formula that handles for one-dimensional system. So, but one-dimensional system, like I said earlier, is just for us to be able to, it's for us to be able to have a simple way of understanding the system. Our world is 3-dimensional. So the expression for expectation energy, and the partition function that we spoke about in 1 dimension will now be extended to 3 dimensions. So the expectation energy becomes, for a 3-dimensional system, becomes E subscripts NX, NY, and NZ, while the partition function is described with Z subscript 3D. And one simple thing you will notice here is that we've been able to obtain Z subscript 1D So by cubing, a cube of Z1D will give us Z3D. So if you had wanted to start with Z3D, it may be very difficult to understand even what we are doing. But we were starting simply by determining what should be our partition function in Z1D. Then we can just cube it to have what we will obtain at Z3D. And something similar applies also in the expectation energy, the energy of the harmonic oscillator. Before we spoke about the energy of one of the harmonic oscillator in one dimension. Now, for three-dimensional system, we can have something that we can really work with. Okay, so we have our expectation energy related expectation energy, which is as good as 3 times what we had in one-dimensional system. So for the expectation energy in equation 1.15 is telling us that this is the energy that the expectation energy for a 3-dimensional system. And for this particular expression, we can differentiate with respect to temperature and obtain our specific heat capacity for a real system. Because one-dimensional system is like an arbitrary, something that is arbitrary, but helps us to solve something that is simple. But now the world is simpler than having our expressions in one dimension. So for a 3-dimensional system, we are going to be needing an expression as equation 1.15 to help us describe the expectation energy. And since we know the expectation energy, and we also have at the back of our mind that C is equal to differential of the expectation energy with respect to temperature, then it's as good as we differentiating this expression to so equation 1.16 is what we obtained from Einstein's model. And this 1.16, we need to now remind ourselves, why did we come to Einstein's model? The answer is, for Boltzmann's model, it could not account for the specific heat capacities at low temperatures. That is why that is the loophole that Einstein found, and he has tried to find a solution to by the use of quantum mechanics. And now, so we need to test: is this expression, is it going to work for solids at both low temperatures and room temperatures? That leads to the 2 limiting cases we have here. And the 2 limiting cases is saying that when KBT is far less than H bar omega. And the second one is when KBT is far greater than H bar omega. When KBT is far less than H bar omega, then we are saying that we are talking about at low temperatures. At least this T, you are familiar with T. That is when T is very small, what will be the specific heat capacity? And when T is very large, what will be the specific heat capacity? T very large in this situation is talking about at room temperature, while T very small in this case is talking about tens of Kelvin. So the next thing we'll do is to now try to estimate that when H cross omega is very large compared to KBT, You're also going to consider in the other limited case where KBT is very large compared to H cross omega. So at low temperature, when KBT is far less than H cross omega, we can substitute and we have this expression for specific heat capacity at low temperature. And what we'll observe is that the answer we have here is not the usual Dulong-Pettit law that says C equal to 3 kb. Let me say C over N. So this one is not saying C over N. C over N is not 3 kb in this case. In fact, C over N, the temperature here is the specific capacity here is depending on an exponential of temperature. So for that reason, we can really say that at low temperatures, C over N is not 3 kb. C over N, specific heat capacity, is related to an exponential of temperature at low temperatures. Then what happens at high temperature? At high temperature, exponential H cross omega, we can find a mini solution to an approximate value for exponential H bar omega over KBT. And that can be done using this expansion. This should be binomial expansion. And from the binomial expansion theorem, we can easily substitute these values and say the first value when n is equal to 0, we have 1. When n is equal to 1, we have H bar omega over KBT raised to power 1, which is what we have here, divided by 1 factorial, which is also 1. When we want to go further by saying what will be the next thing, we can say H bar omega divided by KBT raised to power. Now n will be 2 divided by 2 factorial, which is 2, plus, when we want to go to the third value, we'll say H cross omega over KBT raised to power 3 divided by 3 factorial, that is 6, and on and on. But now we are talking about at high temperature where H cross omega is very small. H cross omega is very small. H cross omega is very small. When H cross omega is very small, then H cross omega square will also be very, very small. And when we are saying H cross omega is small, we're also saying temperature is high. So when we say H cross omega is small, temperature is high, we are now dividing what is small divided by what is large. We should all expect to get something that is very small. And that thing that is very small, when we square it, we'll get something that is very, very, very small. And even we'll now even go ahead to divide again by 2 factorial or 3 factorial, as the case may be. So in a case like this, it is very convenient to say this value here will be approximately 0. Approximately 0. And if it's approximately 0, then we don't have to bother ourselves with things that are approximately 0. So now substituting this value 1 plus H cross omega divided by KBT, substituting this value for exponential H bar omega over KBT in this expression, 1.16, it is easy for us to now come to the conclusion to say that when we put that in here, that is when we replace this exponential A cross omega over KBT, when we replace with 1 plus, replace with 1 plus H bar omega over KBT. When we put, wherever we find, when we put this, what I've written here, when we put it in place of exponential H bar omega over KBT, it is going to reduce to approximate value we would obtain will be 3 KB. I would like you to try that after the class. We are going to have C over N equal to 3 KB. And that shows that at high temperatures or at room temperatures, the Einstein's model can be approximated to give us the law of Dulong-Petit. So fine, so far, we have been able to, Einstein's model has been able to tell us that at high temperatures, the law of Dulong-Petit holds, but at low temperatures, the law of Dulong-Petit do not hold. Instead of we having 3 KB, we are having, values that are exponentially related to temperature. But it has failed to tell us why is diamond, why is it having a low specific heat capacity even at room temperature. Then that takes us to further understanding of the Einstein's model, which we can come to this, our very familiar equation, H bar omega equal to KBT, to say that the T here will be Einstein's temperature when omega is Einstein's frequency. Then the answer to that question is to say that the difference between the materials like diamond with respect to others is the Einstein's frequency. How do we define this frequency? A convenient way to describe the frequency is to talk about what we must have learned while discussing sound. This is an expression that relates frequency with a spring constant and mass. Diamond is known to be very hard material. Diamond is a hard material, meaning that the spring constant is very large, and diamond belongs to is the 6th element on the periodic table. It is a light element. It has, the molar mass is about 12, which is among the lightest materials we have in nature. So that means the M here is very small. So a large value divided by a very small value gives us a very, very large value compared to other materials. And that is what is responsible. That is one of the unique property about diamond, which is carbon. Please excuse me. So that is the unique thing about a diamond, because diamond is very hard and it's also very light. And the graph I have here tells us the predicted value of specific heat capacity of diamond and that of Einstein's model. And when you look at this, even at low temperatures, you say, wow, this is very good. But it is very good, but not very, very good. It is not very, very good in the sense that at low temperatures, specific heat capacity has been known to depend on temperature cube, and not exponential of temperature. Temperature cube, not exponential of temperature. And that is led to more work by Debye, who also used another approach to study specific heat capacities. And in his study, the work was to say that for Einstein's model, put something on it, for both Boltzmann and Einstein's model, they spoke about an atom in the potential world that is oscillating to and fro. Boltzmann thought about the same thing. Einstein thought about the same thing, but with a quantum mechanical approach. But the Debye method or approach was a bit different. He considered the neighbors of the atom, that and at the atom at the bottom of the potential would oscillate, and it will oscillate, hit the next atom, and the next atom will hit the next one. So the oscillation should not be an independent thing. When it's oscillating, it should affect its neighbors, and that is the unique thing about device approach. And another thing about the device approach is that it tried to relate to quantize vibration. It tried to use Max Planck, what Max Planck did to light, Debye tried to do the same thing to sound. So that is also one of the unique things about our device model, which we'll be saying shortly. So similar to what I've asked, similar to Einstein's model, sorry, please. We have, similar to Einstein's model, we have the expectation energy to be similar, one-dimensional harmonic oscillator. So, but what is new here is we're now talking about each vibrational mode. So determination of the energy at each vibrational mode, and after knowing the vibration, the energy of each vibrational mode, we now add all the energies of all the modes together to give us the total expectation energy. And the simple way to do this is to think about a one-dimensional box. I know it may sound strange. We say something is one-dimensional. When you're talking about one-dimensional, you should be thinking about a line, something like a wire. But now we're talking about box and one-dimensional. Somehow it doesn't make sense. But the sense that it will make is that when you can describe it in one dimension, you can easily extrapolate it to higher dimensions. So now we're talking about a one-dimensional box of length L. So imagine you have a box of length L, which is in one dimension, and you turn it to form a circle. So the circumference of this circle will remain as L. The dimension of this, the circumference of this circle will remain as L. And so whenever you are at a particular point and you travel a distance L, you will return to that particular point. So if you travel a distance 2L, you still return there. So when you travel a distance NL, where N is an integer, you will always return to that particular point. So I've tried to make the notes as simple as possible. So I would appreciate questions whenever we meet in class, questions on the forum, on the discussion forum, on the LMS side, questions via email, but I prefer that discussion side so that whenever somebody asks a question, it may help some other people to catch up. And maybe I should introduce a bonus mark for the first person that will post a question on the discussion board. I think I only have somebody that has a bonus mark for the class so far. But I'm still thinking about that. I've not said it anyway. So what I've just said about the one-dimensional box turned into a circle is what this expression is trying to tell you. And so if we require to from now is the wave vector. If it's strange to you, please let me know. From the sum over all possible k of large enough L, we can replace the sum by L over 2 pi. We can replace the sum by L over 2 pi and an integral decay. So the summation of all the possible wave vectors can be replaced by L over 2 pi and an integral decay. So for a 3D box, so now if we can talk about a 1D box, easily we can move on to 3D box. So having the knowledge of 1D, having it cubed, you can easily describe a 3D box. And there is also something I want you to observe here. The K here is bold compared to the K you have here, and it's because this was also cubed. That is why this is bold. So it is not just they are not the same. So this decay can be decomposed to give us decay x, decay y, and decay z. So, and that leads us to this particular expression: L cubed is as good as volume, and the denominator remains, and decay times decay times decay, you can call it the cube k. So the idea is the ability to count the number of modes we have in a box, ability to count the number of vibrations available, permissible, possible vibrations within the box. And with that knowledge, it will help in having the total energy of the system. And when we know the total energy of the system, the next thing is to differentiate with respect to temperature to determine the specific heat capacity. So you can go through what we have on this page. It's just trying to say the different steps made by Dubai. I've tried to make them as simple as possible. Whenever you see numbers like this 18 is referring you to look at the bottom of the page. 18 and 19 is telling you to look at the bottom of the page. There is an information 18, yeah, which is saying that, for instance, in this situation, this is similar to Planck's result for quantum energy of light waves. However, so whenever you see footnotes, I will advise you pause and go to the bottom of the page and read what information do we have there that may be useful in understanding the subject matter. Okay, so let's move back a bit and talk about. So in the course of trying to estimate the total energy, some bunch of constants were put together and they were labeled omega d, and omega d is called the Debye frequency, which we'll see very soon. So some bunch of constants were brought together to give omega d, and g of omega here is the density of state. And the density of state, g of omega d omega, has been defined as the total number of oscillation modes with frequency between omega and omega plus d omega. So omega is a particular frequency, while omega plus d omega is another frequency. So the number of modes, the number of possible vibration states between omega and omega plus d omega is what is defined in this context as density of states. So we'll be seeing different density of states as this course goes on. But for now, for the Debye's model, the density of states is talking about number of oscillation modes with frequency within this range. And the density of state has been defined as omega d cube, which is the Debye frequency has been defined as 6 pi n nu cube. Nu here is velocity, n is okay, so sorry for. So if we go through the equations one after the other, we would have equation 1.27, and equation 1.27 tells us the total energy with respect to the bi-frequency cube. And what we have as TIV are some constants or some values that are not depending on temperature. Our goal is to determine specific heat capacity. So whatsoever value that will be differentiating, which will not be depending on temperature, will vanish. It will be zero. So there is no point writing irrelevant expressions that would will still amount to zero. That is why it has been represented here as TIV, that is temperature independent values. So, the origin of the temperature independent values came from this equation 1.25. Equation 1.25 here, when you look at this expression, if you attempt to expand this expression, everything you have here would multiply this half. And everything you have here, this G of omega, D omega, H plus omega, they are not depending on temperature. So when you multiply it by half, it will not depend on temperature. When you integrate, it will not have temperature. And when you eventually differentiate, it will still not have, it's not having temperature. When you differentiate with respect to temperature, it will be zero. So the only thing here that is a function of temperature is the first term in this bracket. So whatsoever we have multiplied with half gave the temperature independent values that you have seen in the next page. So how did we solve this expression is explained at the lower end of this page. It's like a stepwise. I suggest you go through. By the use of Riemann-Zeta function, we're able to solve this integral. And so, but let's concern ourselves with the results. The results we have obtained is now tells us that when we differentiate the energy with respect to temperature, we have this expression. This is the major expression of interest now, which is the specific heat capacity. When we look at this specific heat capacity, the first thing you will notice is that it depends on temperature cubed. So it depends on temperature cubed and not exponential temperature. Then we can say this is superior to Einstein's model. But another loophole you will see here is that this particular expression, by the time you begin to increase the temperature, the specific heat capacity will continue to increase by a factor of temperature cube. Even when you get to room temperature, it will continue to increase and increase even beyond 3 kb. So when it increases beyond 3 kb, then it becomes worse than Einstein's model. Because like I said before, the specific heat capacity, the specific heat capacity should be something of this nature. So I will say this is temperature. Well, as temperature is increasing, we expect the specific heat. So let me label this part too. This is C over N. We expect the specific heat to continue to increase, but when it gets to a certain temperature, it should remain fixed, constant. It should no longer increase anymore. But if you look at that device model, it will continue to increase, and it will mean that all efforts has been wasted. So, and further with this graph, this something around here should be the room temperature. Let me say T room. And when you trace what you have here from here, when you trace it to this axis, the value here should be what? 3 kb. The value here should be 3 kb. So, but for device model, it is telling us that it will continue to increase even beyond 3 kb. As long as you continue to increase the temperature, it will continue to increase. And that is like a disadvantage. Yes, it's like a disadvantage. So how do we solve that? And why? What went strong in the device model? What went wrong was that in while trying to solve the integrals, there was an assumption that the integral went from 0 to infinity. 0 to infinity implies that the available frequencies range from 0 to infinity, which is not correct. So the solution was that divide came across was to find a maximum limit by replacing this infinity with an upper limit called omega cutoff, which is the frequency, the highest frequency that can be found in the system. The highest frequency that can be found in the system was set to be omega cutoff. The maximum frequency must have a finite value. Assume that if we into n, the number of modes, when we count the number of modes from 0 to omega cutoff, we should have the 3n particles in the box. Unlike what was used before, while trying to count the number of modes from 0 to infinity, it should amount to infinite number of particles. But we don't have infinite number of particles. We have finite number of particles. So from 0 to omega cutoff, we should have 3n particles. So by introducing that correction, by introducing that correction, we have equation 1.30, and equation 1.30 tells us the total energy, and the total energy now is considering from 0 to an upper limit, not to infinity. And now, just like we did in Einstein's model, we would also do the same to check what will be the temperature, what will be the specific heat capacity at low temperatures, and what will be the specific heat capacity at high temperatures. So at low temperatures, the specific heat capacity, at low temperature, the specific heat capacity was still the same as what we had before talking about correction. It's dependent on T cube. So there is nothing, we had no problem with device model at low temperatures. The only problem we had was at high temperatures. So at high temperatures, we now have to consider what will be the value at high temperatures. So, and the Bose factor at high temperature was estimated to give kb T over H cross omega. And when we substitute that into equation 1.30, we have a value that will give us the total energy. And when we have the total energy, the next thing we do is to differentiate with respect to temperature to obtain the specific heat, which in this case is the law of Dulong-Petit. So C over N equal to 3 kb is the law of Dulong-Petit, which was obtained by differentiating the total energy at high temperature with respect to temperature. So with that correction at high temperature, the Bice model reduced to the law of Dulong-Petit, and at low temperature, the law of at low temperature, the specific heat capacity was related to temperature by cube. that is C was related to temperature cube. So, so for now, the Bayes model remains the big boss in terms of trying to estimate the specific heat capacity. Fine, it is the big boss, but it also has some limitations, or it also has some things that did not really go well. For instance, the introduction of omega cutoff, that is the introduction of the cutoff frequency, omega cutoff, was introduced after observing a failure. So it wasn't like a straightforward approach to say that we should have an upper limit. While deriving the expression, it looked like a good idea that we should, the frequency of the number of modes should be, the available modes should range from 0 to infinity. That was the initial thought. But now trying to introduce omega cutoff and such that the number of modes from 0 to omega cutoff will amount to 3n. It's like what I would call a crooked way to the answer. And some other assumptions were made, which included use of omega equal to nu k. Omega is frequency, nu is velocity, k is wave vector. It is strong at high k, but at least it was used to obtain what we have now. Please, okay, Adedeji, Kende, you can unmute us.
All right, good afternoon, sir.
Okay, good afternoon.
Okay, sir. So I want to ask, after the end of your integration, I saw TIV. Does it mean a constant, or it has something related to another equation entirely?
No, the TIV, you see, it's what it means is that they are part of the equation, but they don't depend on temperature. They don't depend on temperature, because we are not really interested in the energy. Wherever you see that TIV, it will be in an expression for energy. We are not really interested in the energy per se. We are interested in the specific heat capacity. So whatsoever we get for energy, we are still going to differentiate to obtain specific heat capacity. So what is the essence of now writing down some values that will still become zero eventually? That is why we have the TIV there. That will say that this value, they are still going to become zero. There is no point accounting for them. So the essence is to say that these values, they don't depend on temperature. For the fact that they don't depend on temperature, and there is no point keeping them, because we are still going to differentiate with respect to temperature. And whatsoever is not depending on temperature, by the time we're having a partial differential with respect to temperature, it will amount to zero. So if we had not written TIV there, if we had written all the full expression that should be there, it's fine, it will be a good expression for energy. But by the time we now differentiate with respect to temperature, it will be zero. So that is why, just to make our lives easier, that is why they are written.
Sir. So which means I can just give that TIV as a temperature independent variable, sir, right?
Yeah, yes, temperature dependent values, temperature independent values. T for temperature, sir. I for independent, yes.
Okay, sir. Thank you, sir.
Okay. So, that takes me to this beautiful graph. Before, we were celebrating Einstein to have a beautiful graph, but now, when you look at this graph where these particular boxes, these squares, the squares are experimental values, while the dashed lines are Einstein's model, and the black solid line is the Bayes model. If you look at it very well, you would agree that the Bayes model is superior to that of Einstein when we are talking about specific heat capacity. And also, I was talking about one of the shortcomings of the Bayes model, which is that one of the major things is that metals behave differently. Metals still have one term, gamma, that is linear, the gamma T that is linear, that has a linear dependence on specific heat capacity. Fine. Debye has succeeded in showing us the relationship between specific heat capacity and the cube of temperature, and the coefficients of everything relating to temperature cube can be summarized as alpha. But also there is another linear term which is common with metals, and that will take us to the next section of this lesson. So, and that will take us to electrons in metals. Electrons in metals, we have a Drude theory, and we also have a free electron model. So our time is up for now. So maybe next class would discuss on this, but I suggest you go ahead, read. Let us have discussions on about this on all the platforms we have available to us, so that by the time we meet again next class, it will be very easy for us to move very quickly, as we still have a long way to go. I don't know what session we are, the week we are in the semester, but this is lesson 1, and we are going to
6th week, sir.
We have spent how many weeks?
This is the 6th week.
6th week, okay. So this is the 6th week, and now we are in lesson 1. And so we'll take it one lesson per week, but it's good you also work hard, try to read, ask questions, then we'll move very fast. Like everything I've written in this courseware, where you read, when you get to, for instance, in this page now, when you get to this, you scroll down, check what is 22 saying. So they provide more information that you may need per line. So Ebube, please, okay, straight to the point. You don't have to greet me. We have greeted ourselves earlier. I'm listening, Ebube.
Okay, so the assignment you gave on our LMS page.
Okay.
How are we going to submit it? I'll submit it to an email. Don't submit it there.
No, you answer over there. You answer on the LMS page. When you click it, you'll see it's very straightforward. You would be able to answer easily.
Okay, sir. Thank you, sir.
Yeah, so some people have submitted. You can ask from your classmates, how did they go about it?
Okay, sir. Thank you, sir.
Thank you. Okay, so I think, is there any other question before we end the class? Okay, bye-bye.